Hello, everyone, and welcome to today's installment of the Trenchless Technology webinar series. My name is Mike Kesdy. I'm the Managing Editor for Trenchless Technology and Trenchless Technology Canada magazines, and I'll be serving as your host for the next hour. We're going to take a quick poll, so please submit your answer and then click the blue Return to Presentation button. I'd like to take this time to remind everyone that any views or opinions presented in this webcast are solely those of the presenters and do not necessarily represent those of Benjamin Media Inc., the publisher of Trenchless Technology, nor does Benjamin Media Inc. endorse any products or methods presented. Today's webinar, sponsored by Vortex companies, focuses on polymerics for rehabilitation and preventative maintenance. This presentation will focus on the evolution of epoxies for both water and wastewater applications, its versatility, performance attributes, and where they're being used with success. I encourage everyone who's live with us to take notes, and if you have questions, type them in, and we'll try to get those answered at the end of today's presentation or via email following the webinar. Allow me to introduce today's presenter, Brock Stone, Vice President of Product Development at Vortex Companies. As Vice President of Product Development, Brock is charged with overseeing QA/QC, product and equipment development, and technical support of Vortex's line of polymeric materials for the water and wastewater infrastructure market. Brock brings 16 plus years of development and application experience in open cut and trenchless applications. Over the course of his career, Brock has used polymerics successfully in both above and below ground structures on a broad range of substrates in some of the most extreme conditions. He is also a NACE certified level 2 inspector. With that, the show is yours, Brock.
All right, thank you, Mike. I appreciate the introduction, and thanks everybody for joining us today. As Mike said, my name is Brock Stone, or Brocklin Stone, and I'm the VP of Product Development for Vortex Companies. Today we're going to be talking about polymeric coatings for use in water and wastewater infrastructure rehabilitation and as a preventive maintenance solution. When we talk about polymeric coatings, we're going to be talking about epoxies. So really, first things first, right? What are epoxies? In its most simplistic form, epoxies are thermosetting polymers, right? And they're formed by the reaction of an epoxy resin curing with a hardener. And inherently, epoxies have great adhesive properties and chemical resistant properties, and they're very durable. But because not everybody on this webinar knows exactly what they are, including myself, because I do get to work with formulators and chemists that get to they have a much better knowledge of these materials. I just kind of want to break down what these materials are for everybody that's joined us today. So what is this stuff? When we talked about it, it's a thermosetting material, right? Thermosetting polymers. But really what it is we've got an epoxy resin on one side and a hardener on the other side. And we get those two together, and they go through a process where they cross-link and become the epoxy itself, or the cured epoxy. And so when we're looking at an epoxy resin, the resin side of it is going to be a bisphenol and an epichlorohydrin. And the bisphenol family has several different bisphenol, but for what we're talking about today, we'll talk about a bisphenol and an epichlorohydrin. And then on the hardener side, we get to what's called an amine. Amines act as our hardener, our curing agent. When we put these two things together, the resin and the hardener, what we get is an exothermic reaction, and that creates this cross-linking between the two. And then what happens through that cross-linking and curing process is we basically produce a molded plastic, or a thermoplastic. Now, that's in its most simple form. But what we do, and many of our competitors as well out there on the market, is we add fillers to this chemistry. By adding fillers to the chemistry, we're able to do things with the baseline epoxy resin and hardener that will allow for increased thickness, increased physical properties, increased and improved adhesion, sag resistance, and cost effectiveness, and reduced shrinking. And so by adding our fillers in and rheology modifiers into our formulas, we're able to produce these materials, these epoxies, these polymeric materials for the water and wastewater infrastructure world. So the end result for us at Vortex Companies is that we get Structure Guard and Structure Guard Water, which are 100% solids, high build protective coatings. Structure guard itself is a workhorse material for us. The structure guard, and I do want to note that we do make, about 130 different polymeric materials, from high build coatings to CIPP resins to polyurethane grouts and everything in between. But for the purpose of this presentation and what we're talking about, we're going to talk about two sets of these materials. One being our structure guard material, which is 100% solids high build, like we talked about. It's chemical resistant. It's got H2S impermeability, and it's applied using plural component spray equipment, heated plural component spray equipment. It's great for use in all sorts of infrastructure, from manholes to wastewater treatment facilities, pipelines, steel pipes, fiberglass tanks, you name it. And what we formulated it to do really is to provide long-term corrosion protection, chemical resistance, and structural enhancement with this material. The next material that we're going to talk about is our structure guard water. Structure guard water is what it says it is, right? It's in the name. So structure guard water has been designed to exist in the water treatment facility, water treatment market, and it's great for pipes 4 inches and up, and tanks 50 gallons and up, and it's been certified with the NSF 61 potable water certification on both. And then same thing for structure guard water. It's great for steel tanks, potable water tanks, water lines, raw water, transmission lines, and fiberglass tanks, as well as many other different environments and substrates, including steel, like you can see this weir channel here, and then also concrete, where you see that flume as well. And so it's been formulated to provide long-term corrosion protection, right? So as we get into it a little bit further, we're going to talk about the benefits of epoxy, right, as a preventive and also as a repair material. And so the benefits of epoxy are several. And one of the biggest benefits that we can talk about with epoxies in general is going to be their corrosion resistance. Okay, so when we talk about these materials, and I talked about inherently based on their chemistry, they are corrosion resistant. But with the added fillers and modifiers that we put into our materials, we're able to provide you with a much more robust system. Okay, they're effective barriers against corrosion. They prevent contact with harmful substances, and we all know that corrosion leads to deteriorating infrastructure. And so installing these materials at new build, or installing these materials after a system's been in the ground for a while, is going to provide you with added benefit and decreased degradation of the system itself. As far as chemical resistance goes, we have corrosion resistance and we have chemical resistance. Chemical resistance is important when we're talking about epoxies, specifically when we're using them for wastewater treatment or water treatment, because we use a lot of different chemicals to treat the water or the wastewater in those environments. And so these materials can withstand acids and alkalis, solvents, and oxidizing agents without deteriorating, right? And once again, I mentioned that this material and how it's built, being that it's seamless and that it's monolithic, is going to provide you with an H2S impermeable environment as well on the structured guard side of life. Another key benefit is its impermeability. I've used the word a few different times, but impermeability means a couple different things. One, from the chemical side, when we put it on as a protective coating, and the other from the infiltration and inflow side, when we put it onto a piece of infrastructure, or we install an epoxy onto a piece of infrastructure, we in essence bond to that substrate and create impermeability to any infiltration or inflow that may be creeping through that infrastructure itself. So it's working from both sides, interior and from the exterior as well. So epoxy coatings create that seamless, non-porous, waterproof layer that we're talking about. And then they prevent the penetration of water, moisture, or chemical compounds under the underlaying structure. And wastewater and water treatment facilities where leakage is happening, right? We can stop that leakage into the environment. So we don't want to treat water as well, right, when we're talking about wastewater or water treatment facilities. And so that's an added benefit as well, and it creates that protective barrier. As far as another key benefit goes, hygienic, right? When we're talking about installing these materials, we're talking about installing a material that's very easy to maintain and easy to clean. So when we're putting these in wastewater treatment facilities, whether it's a digester or a clarifier or a weir channel or a laundry or something like that, those facilities have to be maintained. And a lot of times, if you just have bare concrete, you will get a tuberculation on that substrate itself that's very difficult to remove. When you're using epoxies, you create this non-porous substrate that doesn't allow for things to hang on to it. It's almost a defouling property that's inherent. And so with that defouling property on our epoxies, we're able to eliminate the adhesion of other corrosives onto the surface. And if we do get some corrosives onto the surface, we're able to easily clean that using, just the simple water pressure, really, to remove that from the epoxy itself. And then the last key benefit that we're going to talk about with epoxy is its durability and longevity. Epoxies, specifically the epoxies that we design around a 50-year design life. But epoxies are incredibly durable. If you were to mix our epoxy in a cup, put it out into the environment, it's going to remain cured for as long as we're all alive and past that. But when you put it into a water environment or a wastewater environment, we want to make sure that we're providing you with a robust material that's going to withstand those environments specifically. And so the durability and longevity of these types of products is absolutely key. Additionally, with durability and longevity, we talk about mechanical stresses that these materials can withstand as well. They have a certain amount of elongation, they have a certain amount of hardness to them, and that allows them actually to operate in systems that have some movement to them, whether it's thermal or other. And so durability and longevity, absolutely key. As far as the evolution of epoxies goes, these materials themselves have been around for a very long time, but when they were first brought into the water and wastewater fields or markets, they were brought in a very antiquated form. They were used as basically barriers at best, almost like a paint, and they were very thin build. They were also pretty dangerous back in the day. We still use some of these materials today, but for the most part, we've worked away from some of the materials that have styrenes in them, VOCs, HAPs, and other. And so by using these materials, these 100% solids materials that have no VOCs, that have no HAPs, that have no styrenes, we're using a safer material. This slide, for instance, shows the evolution in itself. On the left there, you see a person that's actually installing coal tar onto a tank. And then on the right, you see the installation of the structure guard material into a manhole environment. So through the evolution of epoxy, what we've been able to do is make these protective coatings. So like I already told you, they're very durable and they've got great performance, but we are also able to offer superior protection against that chemical attack in these environments. And then, like I mentioned a little bit earlier, we have a resistance to those mechanical stresses. And so that evolution has allowed us to go from a very thin build coating that didn't last very long in these environments to a high build coating, which up to 250 mils in a single pass in these environments now, and give you about a 50-year design life. Additionally, when we talk about the evolution of epoxy, through technology and through chemistry, advanced chemistry, we've been able to enhance the adhesion qualities and properties of these materials. And so better bonding, better adhesion gives you better performance and better protection, whether it's steel or concrete and the infrastructure that you're talking about. So put all those things together, you're getting a very advanced chemistry and a very advanced material at this stage. I think one of the biggest things that's happened through the evolution of epoxies themselves and these protective coatings is the ability now to go with a self-priming, single application, direct contact material rather than several layers and several coats that were pre-existing, not too long ago. Now, having several coats and several layers did provide the longevity that we needed, but it also allowed for some risk. Anytime that you're adding many layers or additional materials to a coating itself, you run the chance for having some problematic effects on the bonding and the cohesion between those layers. When you're using a single component system where you're self-priming one single application to a substrate, you eliminate most of those risks that are involved. And so as you'll see here in this slide, we talk about the advanced physical properties as well. When you're looking at the evolution, even from 30 years ago to today, the numbers there on the left were much, much lower. In fact, they're probably about in half, comparatively speaking, to where those numbers are now. And then if you look at the representation on the right, with that single coat, we're able to provide you with, a composite qualified, high build, chemical resistant, corrosion resistant, monolithic, adhesive, cohesive material that's self-priming. So all of those are huge benefits in the evolution of epoxy, specifically our Structure Guard and our Structure Guard Water. As far as the versatility of these types of materials go, it's pretty incredible, actually. We've talked about epoxies themselves, and there are many different chemistries on the market, from polyureas to polyurethanes to composite systems and whatnot. But the versatility of epoxies is really amazing. It allows you to, through chemistry and through chemistry change, allow you to go from one environment to another, whether that be water or wastewater, to other structures as well. And we're talking pipe that can be RCP or corrugated metal, to steel casing, to asbestos line pipe, you name it, you can use these types of materials in there. And then larger structures as well, whether it be vertical or horizontal, whether it be underground or whether it be open air. These materials have a great versatility to them. In addition to that, these materials can have additives or additional materials as part of their whole. So these are great materials for composite design if you need an underlayment, a cementitious underlayment, or even a UV protectant as a top coat. When we talk about the best of both worlds with the versatility, we can use these between, like I said, the water and wastewater systems, but then we can also dial them down to be very, very specific. And so they're tailored to those specific environments. But we start with that base chemistry. Our formulators and designers are able to actually take that base chemistry and then tailor it to a specific environment so that you get the best of both worlds out of that epoxy. The other thing that I think is important when talking about the versatility of these types of materials is that you really have like a dual sport, if you would say, if you will, type of material here. We can go, like I mentioned, above ground, underground, on the external side of a tank, internally. You can go with cold weather, hot weather, chemicals, high heat, low temperatures, you name it. And so you really get the best of both worlds when you're using these types of materials. We've already talked about it, that, we go from potable water to, wastewater treatment facilities with this base chemistry. So really, really great stuff as far as that goes. Now, as far as the material goes, it's designed in a lab, right? We design, formulate, and manufacture all of our materials. And that's done under, the guise of extreme quality control, right? So there's eyes on that every step of the way, and there's a very dialed in process so that the material that is manufactured gets to the customer or the client the way that it's supposed to. But that material is really only as good as the preparatory work beforehand, before installing it. So when we get into best practices, when installing these materials, whether it's a manhole or whether it's a clarifier or a digester, the best practices need to be followed in order for you to install this material so that it provides you with the design and the life that it was intended to. So when we talk about best practices, we're talking about what actually works and in what environment. The assessment stage is absolutely key. And this goes from whether we've got a one-off manhole, right, to whether or not we are, in the design phase for a brand new wastewater treatment facility. Thorough assessment of the infrastructure is necessary to identify the areas that require the protective coating or that require the repair. And so assessing is going to involve the condition assessment of the infrastructure. You've got to identify your corrosion and chemical attack potentials, and then you have to determine the requirements of that material, the performance requirements that are going to be necessary for it to exist in that environment. And that's typically something that the owner, right, or the project engineer is going to provide. Through assessment, you're going to get down to the product choice side, right? So after assessment, and we understand exactly what we need, then we can go through the product choice side. And this is where we like to work alongside engineers and asset owners and contractors so that we can provide them with the best choice of product in whatever environment that they're in. But having a proper assessment is the only way for us to provide you with the proper material choice. So one of the things that we do as far as being a manufacturer is we will work right alongside you as well to make those informed decisions, and we become, a part of the project and a part of the solution by doing so. And also by doing so, we can eliminate many of the pitfalls that are inherent when just maybe the copy paste type of specification comes out, where we have another project, but maybe we don't understand the exact qualifications or characteristics of that project. We copy paste, put on a material that maybe shouldn't have been in that environment in the first place. If we're able to work with you on the, beforehand and up front, then we're able to make those informed decisions as the manufacturer and technical experts on this material. The next portion of best practices, I mentioned it earlier, is that prep work. We're working on either new infrastructure or aged existing infrastructure, and each one of those needs to be looked at differently, and each one of those needs to be prepped differently so that the material that we're installing can adhere properly. So when we talk about prep work, we're talking about providing or preparing the surface profile so that it is in agreement with the material that we're adding to it. We want to create surface energies that will allow for these materials to bond cohesively and create that mechanical bond that we're looking for so that we have extreme adhesion to that substrate. A lot of the times we have to do this not just with using high pressure water, but sometimes we're going to need to open up a profile using sandblasting or using multiple methods, power washing, abrasive grinding, sandblasting, dry ice blasting, you name it. But once we've got loose debris off of the surface profiled correctly, and then the surface cleaned correctly, then it's in alignment to accept the next material, which in this case is going to be a protective coating like an epoxy or polymeric material. We've worked really hard to create and define those surface profiles along with the standards that are already existing. When we go through training with our certified applicators or even our internal crews, surface profile and prep is a majority of what we're going over before we install that material. This is just an example of the existing documentation that you can find from Vortex itself on surface prep, and then validating surface preparation prior to installation. So once we've got that surface prepped and we've followed all of those guidelines, now we can get to the application side of it. So application of these materials, and like I said, whether that's going to be in a wastewater treatment facility or whether that's going to be in a sand or in a manhole, needs to be properly adhered to. So we're going to ask that you follow the manufacturer's guidelines for mixing the materials, and that includes what equipment that it's mixed in, right? And at what ratios and at what temperatures as well. Those proportions and temperatures and equipment are key to the proper installation of the material. What we do also is we're very heavy on, and everybody on this call should be, but safety first. When we're talking about these materials and installing them, everyone needs to be protected from any inherent dangers that there may be. And so protective gloves and goggles and respirators and those types of systems are absolutely key as well. And then we apply the epoxy per spec. Usually the specification on a manhole doesn't get above 125 mils, but it can. And if so, then we can build up to 250 mils. But per spec also means that we follow the guidelines on the QA/QC portion and the protocol during the curing process. And so those are typically outlined in design documents themselves. If not, then we have specifications outlined in our manufacturer's submittal packs and documentation. And then finally, that final QC. Once the material has been installed properly, then there's going to be manufactured specified QC protocol to follow to make sure that the material itself is monolithic, that there are no holidays that are in or pinholes in the material itself. If there are anomalies in the material through installation error, then we need to address those and get those fixed before we put something into service. And those are the things that we look at a bare minimum. A lot of times a project document, an asset owner, an engineer will have other ideas on how they want to look at the material itself to make sure that it is in good working condition and sound for them to kick their system back on. And we'll work side by side through that effort as well with asset owner, contractor, and manufacturer, together on that. As far as the material goes, and this really goes for the market space as a whole, we have testing and standards that are pretty much boilerplate across the industry, right? We talk about ASTM standards, and we talk about NSF, and we talk about ICRI. We talk about different standards that we all have to abide by so that we can create a criteria for all of us, so that we can make sure that the asset owner, the end customer, is getting the material and the protection that they've signed up for. So when we talk about ASTM standards in general, and I'm going to talk about those mostly because that's really the standards that we look at side by side and material comparisons, and then what we see most of the time in specifications. We talk about or what they really are adhering to, or those ASTM standards are looking at, is that performance and durability, right? ASTM standards ensure that the epoxy coatings used meet specific performance criteria, such as the resistance to chemical, their abrasion, and other, and that helps to ensure the coatings durability and long-term protection against corrosion. There's regulatory compliance as well that ASTM it notes, and ASTM standards help create those, or help the coating manufacturers anyway comply with strict regulations and testing methods specific to water and wastewater as well. In addition, there's health and safety standards that are inherent in ASTMs, and these help address the health and safety considerations such as low VOCs, we talked about that, the absence of toxic ingredients, and the compliance to the standards. And then finally, the consistency and comparability. Using ASTM standards provides us common language and a common ground for us as manufacturers and customers and regulatory bodies, right, to compare epoxy coatings, right? And this is by specific test method, and we'll get into that in a minute, and performance requirements, so that the accepted criteria for these materials then can exist in the market, and we can have leveled competition across that as well. And then we can also ensure that the performance of these materials is what it is, or is what it said it's going to be. So when we talk about system compatibility, we're talking about ASTM standards that help ensure the epoxy coatings used are compatible with different substrates, application methods, and other coating systems. This is crucial to achieve proper adhesion, like we've already talked about, and to minimize compatibility issues and to maintain the desired coating performance. The tests that we look at, or that we see most often as part of a specification, are usually around these big ones right here: the ASTM D638, 790, 695, and then some adhesion testing, whether it be 7234 or 4541. These specific standards measure different physical properties. The ASTM D638, for instance, measures several things, but the most noted is going to be the tensile strength of a material. And tensile strength is measured by the maximum stress that a material can withstand while being stretched or pulled apart before breaking. In addition to that, we look at the D695 as a representative of materials' physical properties and strength. And the compressive value is just what it says it is. It's the measure of the ability of the material to resist those compressive forces, right? So the force per unit that a specimen can withstand without failure. And then another test that we use, or another standard that we use to make sure that we are an approved material or approved equal, or that we eliminate other materials that may not measure up, is the ASTM D790. This is our flexural strength, also known as the bend strength. It's the material's ability to resist deformation or rupture under load. So very important physical properties here to look at when you're installing a protective coating into an existing system or a new system. These materials can provide you with extreme longevity and durability, but they have to be strong and they have to have high physical properties. The last thing that we're going to look at as far as the ASTM standards go anyway, is the adhesion properties. So adhesion properties, obviously very, very important. How a material bonds to a different substrate is going to be key to its overall performance, longevity, and lifespan in that system. And so by using ASTM D7234 or D4541, we're able to understand that material's actual bonding strength to either concrete or steel. And so typically what we want to see, and what you'll see in our materials, and you noticed that on slides earlier, is that when we're talking about steel itself, our materials create a plus 3,000 PSI bond strength to steel when properly prepared. The substrate is properly prepared. And to concrete, we typically are getting substrate failure. And then when we're not getting substrate failure, we can get up into the 2000s range as far as the PSI goes. Now, PSI or measuring PSI on concrete can be a little bit tricky. Of course, the pull strength is going to be inherent to the concrete's strength as well. So you can get substrate failure, but only get 150 to 200 PSI when on your pull, and that still is a pass as far as we're concerned, as far as did that create the bond necessary. So that we ran through that pretty quickly. I want to make sure that we're leaving some time at the end of the presentation for some potential questions. So please, if you have those, let's get those in. And then right now, what we're going to do is jump into some example projects to give you some real life examples of where this material exists and what type of infrastructure you can use the materials in. So water and wastewater, that's what we're talking about. Here's just a quick demonstration of a manhole. This is actually a new install that's getting epoxy, direct contact epoxy. There's no underlayment in that situation. Right in here, we have, this goes to the versatility of the material. This goes to, its chemical resistance. It goes to its corrosion resistance. This feeds into a lot. But right here is a case study with a wastewater treatment facility. This is the interceptor at the South Valley, Utah plant. And so you can see on the left before and on the right after, but this was all done direct contact, no underlayment here as well. And that process is still ongoing. We're able actually to inspect that often because our manufacturing facilities are here in Utah, just outside of Salt Lake. When we talk about the versatility, we talk about having a material that epoxy materials can do multiple things. In this instance, we're using our NSF 61 approved or certified, coating structure guard water. This is the city of Arvada back in 2019. This is a weir here and a series of flumes that were rehabilitated. This is a great representation of that composite type design where you have, you've assessed the infrastructure itself. After assessing the infrastructure, it was determined that it needed a structural component to it. That structural component being an underlayment that would bring back the structural integrity and the design thickness to the infrastructure prior to installing a protective coating. So a great example of using materials in multiplicity to provide not only structural rehabilitation, but also that protective coating. And so this was a material here in this middle slide. This actually QM1S, which is a Portland-based cement. That underlayment was put on at a 1/2 inch, and then the epoxy top coat at 125. Here we have an example from Memphis, Tennessee. This should be back in 2011 or 2012. This is another composite spec. It was driven by the actual engineered design. And so in this instance, instead of using a Portland-based cement as the underlayment was a calcium aluminate, which is our Alumiliner, plus the structure guard epoxy coating. All the slides that we're showing here either have a reference and or a case study that we can provide to you. And so you can call the asset owner, you can check out those case studies, and we can help you determine whether or not this material is right for maybe your specific project. When we look at some more examples here, we've got Memphis, Tennessee, wastewater, composite spec there. We've got Central Valley Water Reclamation District. This is a siphon that we went into. You can see the deterioration on this left here. You can see what happens when we build it back with a cementitious material, and then of course top coating it with an epoxy. We also have, we've got several of these. We're going to fly through them quickly. I believe we have a bunch of questions, so I definitely want to get to those. This is a City of Sherwood, another manhole rehabilitation spec. In this instance, these were new manholes and new wet wells. So when we went in, we went direct contact with our structure guard. And like I said, this is self-priming. There's no need for a primer. It's direct contact to a properly profiled surface. When we talk about versatility, this is a great example of it. This is an outflow in Florida. So 350-foot long outflow here where we were, dealing with seawater. You can see the barnacles and crustaceans on the actual pipe itself. But after prep work and after mitigation of infiltration and inflow, we were able to install that epoxy. Great project there. This is another example of a composite spec, but this composite spec utilized not only multiplicity of preparatory techniques such as high pressure water blasting and sandblasting, but then we also did a hand application of the Alumiliner followed by the spray application of the structure guard. Here's another example of a flume in Colorado. This is structure guard water, of course. An older environment here, you have the termination of a CIPP liner coming into a structure. We're able to actually marry up and bond to both the cementitious material and the CIPP liner. Great adhesive properties. An example here of a launderer being pre-coated prior to the dome being installed during the construction phase out in Las Vegas here recently. That was actually just last month. There's 3 of these lined up, and all 3 of them were done with the structure guard and the launderers, and the domes have been installed. We go back to 2012 again, City of Memphis. You can see heavy deterioration here, degradation of the system itself. This was a composite spec that needed both Alumiliner and the structure guard in that instance. This is a new build actually out for the city of Las Vegas. There are 4 identical tanks that are 43,000 square feet apiece. Each one of those was done with direct contact after sandblasts, preparatory stage with the structure guard material itself. One of our older projects from 2015, Douglasville, Georgia. You can again see we're all the way back to the rebar, but using an underlayment here and then a top coat of the structure guard, we were able to fully rehabilitate that. And then this is just a pretty picture of some beautiful green epoxy. That's the structure guard and one of our certified applicators. So at this point, I would like to thank you for joining us. I think we've got about 20 minutes left, and hopefully that's enough time for some questions to be fielded.
Great, thanks, Brock. As always, learn something new in each of these webinars, and as Brock mentioned, it's Q&A time. We'll try to get to as many of these questions as we can in the remaining time allotted. Any questions we don't get to will be handled offline via email. So first off, how do you validate the applied coating installed in the structure meets the physical properties listed on the product data sheet?
Yeah, that's a good question. And so our materials are built under, like I said, strict guidelines as far as the manufacturing goes. We also update our testing regularly. So we create samples in the lab, obviously, provide those to a third-party testing agency or agencies, reputable testing agencies, and then we're provided with that information that we list on our technical data. Over the years, you'll notice that the technical data on our structure guard material and specifically has changed as we get new manufacturing methods, or we're able to, up the ante, so to speak, with the physical properties inherent in our material. So we run through that. The other side of it is that once a material has been installed by a certified applicator, we know that that material or that that certified applicator went through a stringent process to make sure that their equipment was vetted, that their application procedures were correct, and that the QC on site was correct as well. There are a few things that we can do on site to make sure that the material is monolithic, doesn't have pinholes, that its adhesion or its bonding is correct. And those are going to be specific to those standards for holiday testing and for pull testing on premises. Not a lot of, and here's the difference between cementitious world and the epoxy world. In the cementitious world, they'll do samples on site. They'll do cylinder samples, or they'll take cube samples, and they'll take those on site from the actual product being installed, and they'll bring it back to a lab, and they'll check for those compressive values and breakpoints and things like that. Really, with the epoxy world and protective coatings in general, we're not held to that, because we have those strict standards beforehand in providing the third-party data that we represent on our technical data sheets.
Cool, thanks. What is the maximum thickness for NSF 61 potable water applications?
That is a good question as well. Typically, for all materials have a different standard associated with them, right? So for our structure guard water, for instance, we're looking at a couple different things there. We're looking at the pipe diameter, and we're looking at tank size to see if we can even put the material in there in this first place. If the pipe is below 4 inches, our material is not certified to go in there, so 4 inches and above. And if the tank is less than 50 gallons, which most tanks aren't less than 50 gallons, so we're not allowed to put our material in there either, but over 50 gallons, we're allowed to put in there. Now, our material specifically was certified at 125 mils. Now, the thickness of that coating, if we were to need additional coating, well, we could do that, but we can't be below 125 mils with our protective coating as certified by NSF.
Great. Speaking of standards, can you confirm that with the name change and merger of NACE and SSPC, that the codes and standards are still NACE XXX and not AMPP, whatever the standard would be?
Yeah. And so that's been an interesting process to work through as well. So, I think AMPP has done a good job with the merger of SSPC and NACE. We're still working through those. A lot of times what's happening, and yes, can we assure? Yes, because the standards aren't changing to a point where it would eliminate. If they are, then there's a different standard that's developed, and we will address that. But for the most part, working with AMPP or working with SSPC, NACE, those types of things, they're in alignment. It does not change. Okay, as far as the standards that we talked about, ASTM is still ASTM. Protocol, NACE standards, or SSPC, when we talk about, if we were talking about SSPC SP1, like solvent washing, right? It's still recognized, and it's now in a new volume as well. So the names are still recognized, and you can still use those standards. But as new standards are developed, our new standards books are developed by AMP, those will be coming out. But they still adhere, and they're still they're still recognized.
Great. So what works are necessary on 40 to 50-year-old structures that have been continually exposed to raw sewage? And it says structures are structurally intact. So
that's good. So something that's been, in the ground for 40 or 50 years is probably, it's time to rehabilitate, that's for sure. But I'll go back to the assessment side. We can't just, say that this, just go direct contact. In fact, that would probably be inappropriate. I would state that if it's 40 to 50 years old and it's in ground and it's a manhole, it's either going to be, concrete, precast concrete, or it's going to be a brick manhole. In either case, at that age, we would expect to see degradation that would necessitate the use of an underlayment, okay, a protective coat or a cementitious underlayment to build back or to either original design thickness or to build back in those sections where the mortar has been eliminated in a brick manhole, so that we can have a nice palette to put epoxy on. But I would say that assessment's going to show you that you're going to need some sort of an underlayment to build it back first, and then an epoxy coating would be sufficient to provide you with the protective coating that you need in that environment. And I'd say, 125 mils is going to be more than sufficient. Another thing is to recognize, and we talk about 125 mils, and it's out there a lot, and it's really derived from the ASTM standards themselves. Most tests that we go through, we have a thickness, and 125 mils is what we submit our materials at. And so that's where we kind of level out the playing field, right? If I submit my materials and competition B submits their materials, and we're both at 125 mils, then that gives the asset owner a measurable right there between the two materials at that certain thickness. So we would state that, underlayment and 125 mils, especially if it's 40 to 50 years old, but we can definitely look at that and rehabilitate that system. That's not a dig and replace to me. That is why trenchless technologies exist. We get to that age of an infrastructure. Let's look at it and then put the best material in the ground to rehabilitate that structure.
Great. Can you expand on UV protection for exterior applications of the products?
Sure. So epoxies themselves, they inherently, and this is based on the chemistry that we talked about earlier, but epoxies will yellow in direct contact with UV. It doesn't create any problems with their chemical or corrosion resistance properties, their physical properties themselves, but they'll slightly yellow. And so some asset owners are also interested in aesthetics. And when you're talking about aesthetics, it's sometimes they want that bright green or that very bright white to remain. When they want something like that, we're able to install a UV protectant top coat if necessary to that epoxy, so that we eliminate the potential for yellowing through exposure to UV. It's not a necessary component, but it's available. And since we design, formulate, and manufacture all materials, we design, formulate, and manufacture that as well. And so we're the materials themselves, the systems themselves are compatible with each other.
Great. So would these be considered a non-structural class 1 liner, or can it be made to class 3 or class 4 structural?
Yeah, so that's an interesting thing about epoxies as a whole. So when we talk about epoxies, I've never stated ever that this is, these are structural, right? Structural is through design. And so when we're talking about getting into a class, when we get into something that is fully structural, that's going to be by design. We believe, and we know this based on the physical properties of the material at 125 mils minimum, right, that we're going to provide structural integrity and a sense of an additional a bit of structural integrity to anything that we put the material on. But if we want fully structural rehabilitation, then we need to look at it from a design approach, and we need to take in all things. All things need to come into consideration, from the size of the structure to, its shape, the ovality, water tables, traffic load, etc., so that we can then design an epoxy to the thickness necessary to give you a fully structural component. Now, we think that, and this is just my opinion, of course, like you mentioned at the beginning, but my opinion is that it's not cost effective to provide a fully structural rehabilitation with epoxy. It's much more cost effective. And it's a better overall product to provide a composite spec, composite design when looking at that. That being said, north of the border up in Canada, we have been faced with several times projects where the epoxy itself was designed as a fully structural. So I think in one of my slides that I showed dollies on that adhesion. Those dollies were actually over an inch thick of epoxy. They were installed into a manhole system, a series of manholes in a system up in Canada. So can it be done? Yes. Is the material as a standalone fully structural? No, but it can reach that through design. I hope that answers that question.
Works for me. We had a couple of questions come in regarding temperatures, so I'm going to kind of lump them together here for you. First of all, any concerns with cold temperatures and high moisture during epoxy application? And then also, what is the temperature range to which these materials can be exposed?
Okay. So yes, always concerned about low temperature and moisture during application. You can get a cold if you don't have a jacket on. Okay, that was just a joke. Here's the deal with cold temperatures. We don't want to install this material at lower than 40 degrees. When we're and that this is the infrastructure itself. The temperature outside can be cold because we can control the temperature of the epoxy, and we can control the temperature of the infrastructure being repaired or rehabilitated, right? So when we can control those two variables, then we're okay with it. But we don't ever want to put this material onto a substrate that's less than 40 degrees. And then when we talk about moisture as well, moisture is kind of a broad term, right? You know, I'm from Colorado. We don't have a lot of moisture, but we do a lot of work in Florida, a lot of moisture. But what's more important actually is a window. And we talk about dew points. What we want to do is stay away from dew being on the surface when we apply. And so through our specification, we have measures, and these are that keep our installers from applying the material within 5 degrees of the dew point. If we can stay 5 degrees outside of the dew point, even if it's down at 40 degrees or, you know, up at, you know, in Las Vegas or Phoenix and 120 degrees, if we can stay outside of that dew point, then we can successfully install the material onto the substrate without it having a problem. If you're inside the dew point when you're installing these types of materials, and I don't care if it's polyurea, polyurethane, or an epoxy, you're going to have a problem at the interface of the substrate and the material being sprayed onto it. Now, we might not be able to see it with our naked eye, but there's moisture there. And if there's enough moisture there, that's going to cause a contaminant problem for bonding of the material to the substrate. So we're very cognizant of that, and it's part of our QA QC process while installing, and our certified installers and and even our own crews adhere to that very closely. If not, you're subject to failure. So you have to watch that. So I think that answered the low temperature and the moisture. And then you said, I believe you're saying the tolerances as well. Like
I believe so. I believe that was the question. Yeah.
Okay. Yeah. And so these materials are installed and can exist in freezing temperatures after they're cured. That's not a problem. And then they can survive in very hot environments as well. I think temperature, though, when we talk about constants, that's one of the things that I think is necessary to talk about. And constant temperature for an epoxy, we design high temperature epoxies that can go well into over 200 degrees Celsius. But for these particular epoxies, Structure Guard and Structure Guard water, we don't want to get over 180 degrees constant in that. We can at that point, when you're above 180 degrees, you can start to soften the material, and we don't want to do that.
You spoke earlier about the surface prep. Here's a question regarding that. If a steel bolted tank has a lot of corrosion pitting on the floor, then do these corrosion pits have to be removed and the rest of the floor be sandblasted prior to the epoxy application?
Yes, we don't want that to be an inhibitor of bonding. So we're going to go into a steel tank, such as that bolted steel tank that's been the example anyway. And anywhere where we have pitting or we have flaking or we have any rust or tuberculation, we want to remove that. We want to get it down actually to near white prior to installation. And using sandblasting methodology or vapor blasting or other, we can achieve that. But yes, you're gonna need to remove that prior to installation.
Okay. How is flexural strength measured for thin coatings? For example, ASTM testing?
So the flexural, I'm gonna go back to that real quick. Oh, sorry, I missed it. So flexural strength is measured using this actual, there's equipment looks almost exactly like this. So what's used is a plate sample, and that plate sample is put between 3 points. Between those 3 points, pressure is put from the top, and you can see in this instance that it starts to bend, right? So flexural strength, known as the bend strength, is measured when it's resistance to deformation, right? So it'll be put under load and that'll sit there for quite a while, but then it'll start to bend. And so when we talk about thin builds, and he said thin build materials, we don't typically install thin build materials. Ours are all high build materials, and we're talking 80 mils minimum is what we have in our specification and up. So with an 80 mil material, which is just 8 thousandths of an inch there, or 8 100ths of an inch, we can measure that using ASTM D790 measuring tools, and through a third party. But that's the system right there.
Great, thanks for flipping back to that slide for everyone. So is it correct that the structural guard product is a single coat system? It does not need a primer, top coat, or multi-coat system, correct?
Yes, that's correct. And so we talked about, the evolution of epoxy. And so that being said, we're able to look at the industry and say, where can we, what are the added benefits for our material? What can we do to make there more benefits? And a much more beneficial material is to be self-priming, right? If we can be a self-priming material that can build to 250 mils in a single application, right? Then that gives an added benefit to everybody installing it. And so that's what we've designed. And that's up to 250 mils. We have guys that are, obviously we're conservative when we talk about this, but 250 mils is not a problem with this type of material, with the rheology modifiers and fillers that we've put into it, and the design really characteristics around the material.
Right. What is the typical curing time for epoxy coatings for manholes or inflow channels?
Yeah, so within 4 hours, this material, the structure guard after application, is going to be substantially cured to where you can go return to service. I will note though that these types of epoxies can continue to cross-link and harden and get to their full cure within 24 hours. So 4 hours you can return to service. 24 hours we would expect that to be absolutely fully cured. But the nice thing about epoxies, and this is inherent in an epoxy technology or chemistry versus a polyurea or polyurethane. Ours epoxies are hydrophobic, right? So if you were to mix this type of an epoxy in a cup, and then you were to pour water on top of it, right? And you'd have the epoxy layer on the bottom and the water on top. It will fully cure with that epoxy on top without having an adverse reaction at all, because it repels water. It's hydrophobic. Whereas another chemistry, polyurea, polyurethane, for instance, if you were to mix it in a cup and pour water into it, it would make foam. So there's a negative reaction to that. But using epoxies, that's why you can return to service. The cure will still continue after it's been returned to service, or moisture is inherent in the infrastructure.
Great. So if you're using a concrete underlayment, how long is the typical cure time before the epoxy coating can be applied?
Yeah, so there's different types of underlayments, and you've got underlayments from Quadex anyway, from Vortex companies, Quadex Repair Materials. Hyperform is an underlayment that can be used, and that's after a Hyperform is installed, you need to wait an hour prior to installation. 2 hours is probably best practice. If you're talking about our QM1S or the Alumaliner or our Geo, then you're talking about 24 hours prior to installation or application of the epoxy. So you would apply the underlayment, QM1S, Alumaliner, or Geocrete on day 1, day 2, then you'd put the epoxy on.
Great. I guess we have time for one more. So what type of environmental controls are required, and how do you know which ones to use according to application, or is there a standard one that you use?
Environmental controls. So I'm assuming that we're talking about safety and other, but I mean, environmental controls. If we're talking about safety, I mean, it's clearly outlined what we'd want to do to make the environment safe. If you're talking about installation, we're talking about temperature, humidity, dew point, and then also the measurable moisture content within a substrate. There's tools for all of these. Simple apps actually can be used on your phone to determine most of this. But then we also have tools that are industry related that can measure these types of things to make sure that we're installing our material in the proper environment. I hope I answered that correctly. If not, I'll email whoever that was and we'll get down to it.
Great, yeah. Thanks, Brock. This was an education-packed hour, and as I mentioned earlier, any questions we didn't get to live will be handled offline via email. Thank you to Vortex Companies for sponsoring today's presentation, and thanks again to Brock for his time. Finally, I'd like to thank all of our viewers for joining us today. As a reminder, any views or opinions presented in this webinar are solely those of the presenters and do not necessarily represent those of Trenchless Technology or Benjamin Media Inc., nor does Benjamin Media Inc. endorse any products or methods presented. If you'd like to refer back to this webinar or share with your colleagues, you can do so at any time by visiting trenchlesstechnology.com/webinars and selecting today's webinar from the on-demand webinars section. The webinar will be available on our website for the next year. As you exit this webinar, there's an opportunity to participate in a parting survey. We appreciate your feedback, and we appreciate everyone for joining us today. Cheers. Everybody have a great day.